We have discussed the fact that sometimes no symbolic method in our arsenal is powerful enough to find a formula solution to a first-order ODE. So we may have a first-order ODE, y prime equal f of ty, and you may perhaps not be able, perhaps can't find a formula solution. It unfortunately happens with some frequency. In that case, we have learned that we can deploy graphical methods, vector fields. And when we do that, we generally can see something about the general nature of solution curves. General nature of solution curves is what we can glean from graphical methods. However, if we have a specific IVP, so that is if we have the differential equation together with some piece of initial data, say y of t0 equal y0, then it may very well be that the graphical methods, that is the vector field, might not be sufficiently concrete in order for us to say anything specific about the one curve that satisfies both conditions. Well, in that case, we then turn to numerical methods. And that's what I want to talk about in this video. A little bit about numerical methods for dealing with initial value problems like that. Well, as it says here, a numerical method is an algorithm for generating two sequences of points, t0 less than t1 less than tn, and corresponding y0, y1 up to yn, with the property that y sub j is approximately equal to phi at tj, where phi is the unique solution of the IVP that you're considering. So we have something like this. Here's your points, t, and then we have corresponding points y. And those points approximate points on the solution curve. So if we join them together somehow, perhaps by straight lines, perhaps by some more sophisticated interpolation method, then that is an approximation to the solution. It may be self-evident, of course, but let me, for the record, point out, of course, that this first point here is the point t0, y0, and that's your given initial data. Future data, of course, is generated by the algorithm. In the notes, you've encountered several different types of numerical methods. You encountered the Euler method, the so-called improved Euler method, and a few other generalizations of the Euler method. Various Runge methods, including the famous Runge-Kutta method. For the record, I'd like to write down the formula for the Euler method, just to recall. Yn plus 1 is equal to Yn plus h f tn Yn, where h is the so-called step size, and it's the difference between the t's. The assumption is that the tj's are equidistant, equally spaced. Now, MATLAB's numerical solver ODE45 is in fact a combination of several very powerful algorithms. It's really state-of-the-art, and we will use it extensively throughout this course. Now, in the remainder of this video, I'm going to do two things. First, I'm going to review a few of the most important aspects and or features of numerical solvers. And then secondly, I'll show you how to use ODE45. So as I said, I'm going to talk first about the aspects of numerical solvers. Perhaps the key component of a solver is the algorithm that it implements. We've already talked about Euler, and the algorithm is expressed in this formula, which generates the approximation points. In this case, the step size is constant. The distance between the points on the t-axis are equidistant. And as I say, that's a constant step size. We then have the improved Euler method, and here's the formula for it. It's a little bit more complicated, and I believe perhaps your instructor explained it. It's also explained in the notes. Again, yn plus 1 depends only on the previous approximation point, yn. But in many of the other techniques, methods, the Runge methods, for example, the n plus first stage, the n plus first approximation may depend upon all the previous steps, not just the immediately preceding one. The next thing I want to address is error. There are two kinds of error, local error and global error. The local error is the error one makes when going in one step. Global error, of course, is the error that is made by going from the start to the finish. It turns out that both of these errors are proportional to a power of the step size. And the power involved is the way that we measure the strength of a method. I'll say more about that in a minute. There are also two components to the error. There's the formula error, the error that you make because the formula is only an approximation to the actual values for the unique solution. The other kind of error is round-off error. We're dealing with a machine with a finite number of bits. It can only keep track of a finite number of places, usually 15 or 16. And so there's a certain amount of round-off error in the computations. And this here is to signify that, generally speaking, the round-off error is minor, insignificant compared to the formula error. Okay, the order of a method is actually the power that appears in the global error. So that's what this references to. The Euler method is first order, improved Euler is second order, Runge-Kutta is fourth order, and ODE45 is actually a combination of fourth and fifth order methods. ODE45, like all modern solvers, employs the method of variable step size. Internally, it knows as it's computing approximations when things are getting very variable or the approximations are varying very widely. It decides on its own to diminish the step size in an attempt to improve accuracy. So modern technique, very, very valuable to have an algorithm which employs variable step size. And finally, the matter of interpolation, I've already indicated when you have a set of points, you can connect them by straight lines, and that resulting graph is your approximation to your graph of the actual solution. There are various more sophisticated methods one can do that. Just think of the situation, you have a bunch of points, take any three of them successive. You can, of course, join them by two polygonal lines, but a more sophisticated method would be to approximate them by the best parabola that fits the curve. And in some sense, that's what goes on in the interpolating methods of ODE45. Finally, I would point out that all of this material is discussed in Chapter 8 of the Differential Equations with MATLAB book. I urge you to consult that, and you'll find some other information there as well. All right, it's time to put ODE45 to use. So in this part of the video, we're going to look at this differential equation. Y prime equal 2 sine t plus e to the minus y cubed, as well as the specific IVP consisting of this equation and the initial data y of 0 equal 2. Now that's a particularly nasty differential equation. It's not amenable to any of our symbolic techniques. And in fact, although I will not evaluate the command, if you attempt to solve it with dsolve, it basically hangs MATLAB. So let's use ODE to numerically solve the initial value problem. Here's the syntax. We define an anonymous function, equal to the right side of the differential equation, and we do it with vectorized notation, and then we invoke ODE45. Before I evaluate the cell, let's explain the syntax. The function f, as I said, expresses the right side of the differential equation, and it's in vector notation so that we'll be able to use ODE on vectors. You'll see that in a moment. The interval on which ODE45 solves the IDP is 0 to 5, and the 2 is here, which expresses the fact that the initial value at t equals 0 is 2. So it's a slightly unusual syntax. You don't have the 0 and 2 together. This is the interval on which the equation is solved, and this is the initial value of the dependent variable at this value of the independent variable. Okay, so let's evaluate this cell. And ODE45 actually solves it and gives you a graph. Let's note the circles indicate the points at which ODE45 computed the approximate solutions, and then ODE45 connects the centers of the circles to form the approximating graph, which then represents the numerical approximation to the solution function on the interval 0 to 5. And let's bring the graph up again. There it is. Okay, so there are other ways to use ODE45. I'm going to do 5 of them here. To get a table of values, to get values at a specified intermediate point, to graph a family of solutions corresponding to different initial data, to solve backward in time, and to find a singularity. So we will do these one at a time. Here I'm going to produce a table of values, so the syntax is a little different. Instead of just issuing the command ODE, I set it equal to a vector, and it will produce a table of values. I run the section. In order to see the table, I have to look at the MATLAB window, and there's the table of values from 0 to 5. Okay, let's go back to the M file. Next, the intermediate values. So this time I set it equal to a single output variable, and I use the command deval, which I won't explain here. I'll let you look that up in the MATLAB book. And I'm finding the value of the solution at the number 3.5456. Run the section, go to the MATLAB window, and there's the value, 5.9020. 3.5456 is in here somewhere, and so you see why it was about 5.9. Okay, back to the M file. Multiple initial values. And here's where it's important to have the function be vectorized. I'm going to actually graph the solutions where the initial value is 0. I take it on 0 as -4. All the way up to 2, it's step size 0.2. And we're going to get a whole family of graphs. So this is 6 times, there's about 30 graphs. Let's see. There they are. And look very much like the other one, except here, when we start out down in negative, this is because of the e to the minus y cubed, right? When I have a negative number for y here, minus y cubed is a huge positive number. The curve starts out with a huge positive slope and then goes like this. Okay, so that's why the picture looks like that. I've actually drawn 30 different solutions of the differential equation obtained numerically. I went from 0 to 5. Now I'm going to go to the left. So I'm going to do it again. I'm going to go further out this time and also go to the left. So that is solve backwards in time. So here's the same as before, except I went out to 10. And here I issue a separate command going to -10, and I plot the two of them successively. That's the reason for the hold on. So let's evaluate the cell. And there's the graph. Looks like a sinusoidal, and I'll let you think about that as to why it is. The exponential term goes away eventually, or it becomes very insignificant, and the graph is pretty much like y prime equal 2 sine t in the long run. Okay, and notice I went to backwards as well as forwards. And finally, how can we find a singularity? Well, now it's changed drastically if you start with a negative value of y at t equals 0. Then that e to the minus y cubed is a huge positive number, and the exponential term causes things to blow up rather swiftly. And NumMethode45 essentially finds the singularity. So now I'm going backwards. I started out with y of 0 equal minus 1, and I try to solve from 0 to minus 0.1. You'll see we don't get there. NumMethode45 says things are starting to get very dicey at minus 0.08, and in fact, there's a singularity very close to that value. Final comment is, for more information on NumMethode45, how to use it, see the book, Differential Equations with MATLAB by Hunt et al.